So we can start with the next speaker. It's a great pleasure to have Paolo Ballerini here from Torino. He's going to tell us about integrated correlators, but in N equal to Q.
Yeah. Thanks, Daniele, for the invitation and for giving me the opportunity to speak here. I will talk about some recent developments in the study of integrated correlators in N equal to superconformal gauge theories. And what I'm going to say is mainly based on this work done in collaboration with Bill Lofro and Lerda from Torino and Alessandro Pini, who is here in the audience from Humboldt University. So as Daniele explained us in the morning, the study of integrated correlators is a very fruitful framework where to study non-perturbative effects in four-dimensional superconformal gauge theories. And just to quickly remind you, even if we have just listened to it, the basic idea of these integrated correlators is that we can take four appropriate derivatives of the log of the partition function of the N equal 2 star gauge theory, which is the mass deformation of the N equal 4, and these derivatives can be taken with respect to the complexified Yamnitz coupling and to the mass of the adjoint hyper. And this gives us information about the four-point functions of superprimal operators in N equal 4 super-Yamnitz theory, integrated over a specific measure which is fixed by superconformal symmetry. And the first correlator that, as Daniele explained us, was with the two derivatives with respect to the complexified coupling and with respect to the mass. Later also, this other kind of correlators that I'm showing here was derived and with all the derivatives with respect to the mass of the adjoint hyper in this mass deformation of N equal 4. And then after these very important results, many aspects of this observable have been investigated. Of course, the large N expansion, but then also the large charge limit, the exact and modular properties as discussed in the morning, and so on. But what makes this topic very interesting is that it can be studied by using very different techniques, such as supersymmetric localization, but also conformal bootstrap, modularity, resurgence, and even the usual standard Feynman diagrams, and even superstring amplitude techniques. Indeed, these superprimal operators in these four-point functions of N equal 4 in the large N limit are dual to some gravitons on superstring type 2B superstring theory, and so evaluating these four-point functions of superprimal operators gives constraints on the dual scattering amplitudes of gravitons on ADS5 x S5. So more recently, much progress has also been made in the study of integrated correlators in less supersymmetric setups, so in N equal 2 superconformal gauge theories. And in particular, the first example where these kind of correlators were studied in an N equal 2 context was by Behan, Chester, and Ferrero, and was this model, with this model which is N equal 2 superconformal gauge theory with SPN gauge group, one antisymmetric hyper, and four fundamentals 1 with an SO8 flavor symmetry. So this model is very interesting because it can be studied, can be engineered in superstring theory by taking ND3 branes in an O7 plane background with 4 D7 branes plus the 4 orientifold images. So we have a D7 brane sector, and in this D7 brane sector, we can consider some open string states attached to the D7 branes. And in particular, the gauge group on the D7 brane work volume theory is the same of the flavor symmetry group of the dual CFT. So these string states transform in the SO8 gauge group, and so they showed that by studying some four-point functions of flavor multiplets, one is able to put some constraints on the scattering of SO8 open string gluons on ADS5 x S3 this time, where these states propagate in the large N limit. So we considered a different N equal 2 gauge theory, which we call D theory, and this time it has SO8 gauge group with 2 antisymmetric hypers, 4 fundamentals 1, and in this case, the flavor symmetry is U4. So also this model, of course, can be engineered in superstring theory by taking n fractional D3 branes in a Z2 orbifold, probing the O7 orientifold background with the 4 D branes plus their images. So in this case, what changes in this configuration is that the flavor symmetry is now U4 instead of SO8, and so also the gauge group on the D7 brane volume theory is now U4. So by studying this integrated correlator in the dual CFT, one can get constraints, this time on U4 string gluons. So that's the idea. And so these U4 gluons in the CFT are dual to the usually called moment map operators that belong to the flavor current multiplet. These are operators of conformal dimension 2 and are bilinear in the scalar fields of the fundamental hypers of the model and transforming the adjoint representation of U4 of the flavor symmetry for the CFT. So the idea is that we consider a mass deformation of this model by giving 4 different masses to all the four fundamental hypers. And if we take 4 mass derivatives of the log of the partition function of this mass deformation, what we get is a 4-point functions of these moment map operators, which is integrated still over a measure, which was found in a paper by Chester a couple of years ago, where he generalized the case of the measure for a generic 4D n=2 gauge theory. So from now on, I will concentrate on the left-hand side of this relation. So we will see how to evaluate these 4 mass derivatives of the log of the partition function in this n=2 model. And we know that we will get these 4-point functions of moment map operators integrated over the measure, which consequently gives constraints on the dual amplitudes of gluons, of string gluons. So far we have seen 2 different n=2 models, and they seem to be very similar because, of course, the integrated correlators studied in these 2 models give constraints on dual amplitudes of gluons. In one case we have SO8, in the other case we have U4. So what we expected is that the strong coupling in the larger limit of these models should give similar results. Of course, not the same because the gauge group is different, but similar results. But at weak coupling, the CFTs are completely different. We have different gauge groups, we have different flavor symmetry groups, different matter content, and on top of that, as we're going to see in a moment, the matrix model description of this theory is way more involved. Indeed, from the work of Pestun of 2007, we know I'm working just in the 't Hooft limit, so I'm neglecting the instantons. We know that the partition function of n=2 gauge theory in 4 dimension, when we place the theory on a sphere S4, by using supersymmetric localization, it is given just by an integral over some n by n Hermitian matrices. And in particular, each 4-dimensional n=2 gauge theory has its own exponential weight. And the exponential weight is given by this interaction action that in the case of the D theory is given by these 2 terms. The first one is a single trace deformation, as you can see, and it is exactly the same interaction action of the SPN theory. So, of course, here the traces are taken in the SUN algebra instead of the SPN, but the formal expression is exactly the same. But here, we also have another term that this time is a double trace deformation. And this turns out to be exactly the same interaction action of a different n=2 SUN gauge theory that contains 1 symmetric plus 1 antisymmetric hypermultiplet. So that's why the matrix model of this theory is quite more involved, because it has not only single trace deformation, but also double trace deformation. So to deal with this kind of matrix model, interacting matrix model, the easiest way is to perform a change of basis between the basis of the traces of these Hermitian matrices to a new set of operators, which we call P operators. This family of operators is orthonormal in the larger limit of the Gaussian matrix model. And as proved in this paper by Beccaria, Billo, Galvagno, Hazan, and Lerda of 2020, by doing this change of basis, and of course after some algebra, one is able to find an exact expression in lambda for the interaction action. So the double trace part now is written in terms of this convolution of Bessel functions, which, where all the dependence on the coupling is resummed inside these arguments of Bessel functions. We did the same also for the single trace part in this case, because we also have the single trace deformation. And in this case, it can be written in this way, where this y is still an integral of a Bessel function, as you can see. So I stress again that if you look before the interaction action, its dependence on the 't Hooft coupling lambda was given through a perturbative series. Now, instead, we can deal with an expression which is exact in the coupling. So that's the very important point. So I cannot give you many details about the computations in the matrix model because of time, but once that one have a matrix model and have an exact expression for the interaction action in lambda, it is also possible to study the correlation functions of these P operators in the large N limit, and these are the results for the first orders in the large N expansion, and to get exact expressions also for these correlation functions. As you can see, these expressions are exact in the coupling and are written in terms of these objects. And I'm showing the 1 and 2 point functions because they will be useful in a moment. Indeed, actually, we're interested in the mass deformation of the D theory. So now we give for different masses to all the fundamental hypermultiplets of the theory, and we do a small mass expansion of the partition function of the D theory, and we stop at the quartic order because we're just interested in 4 mass derivatives, and then we set all the masses to 0. So by doing this small mass expansion, what we get is that we have the exponential of these 2 operators that are S2 and S4. I'm not showing them in terms of the traces because they have quite complicated expressions, but you just need to know that they are single trace deformations. So now one can prove that all the possibilities of the mass derivatives that one can consider in these, for these U4 moment map operators are the 3 following combinations. In particular, the third one is vanishing because we don't have a structure like this in this expansion, but we still have to evaluate these first 2 combinations of the mass derivatives of the free energy of the T-star theory. But as you can see, this problem is now reduced to the evaluation of these vacuum expectation values of these operators in the interactive matrix model of the D theory. So now what we still have to do is to write S2 and S4 in terms of these P operators, and these are the results for the first orders in the large N expansion. And so now that they are written in terms of the P operators, as I showed you a couple of slides before, we know how to evaluate the 1 and 2 point functions of these P operators in the interactive matrix model of the D theory. And so once that we have these results and putting together with the results for the 1 and 2 point functions of the P operators, one is able to find the exact expressions of the mass derivatives of this model. And in particular, once that one has the exact expression, as you have seen, all these expressions are written in terms of integrals of Bessel functions of the first kind. So the easiest way to study the strong coupling of these kind of objects is to employ the Mellin-Bars method. So by using this method, one is able to find these strong coupling expansions, and in particular, we found the first 3 orders in the large N expansion, and these are the results. So as expected, these strong coupling expansions are very similar to the one found in the SPN theory, and so it is what we expected to find because we are still putting constraints on dual gluon amplitudes on ADS. But if we take the exact expression and we study it perturbatively, of course we get completely different results from the SPN theory because, of course, the CFTs are very different. And also the matrix model description, as we have seen, is completely different because here we have also the effect of double traces that in some way in the strong coupling regime cancels out. So just to conclude, we managed to find the first 3 orders in the large N expansions for these mass derivatives, so for these integrated correlators. And of course, it would be very interesting to try to go beyond the first 3 orders in the large N expansion. In the case of the SPN theory, they managed to do that because in matrix models with just with single trace deformation, they found that the partition functions satisfy a set of total lattice equations that can be used to fix also subleading orders, more subleading orders in the large N expansion. Here it seems more difficult to find a structure like that, but it can be. And then, of course, it would be very interesting and very important also to study the large N limit at fixed Yang-Mills coupling, because here we concentrated on the Toft limit, but if we fix the Yang-Mills coupling instead of the Toft coupling, of course, also the instantons have to be considered. And so one could check if the large N behavior of the instantons provide completion for the perturbative results at strong coupling found here, and maybe into some modular functions. That would be great. And finally, another non-perturbative effect that we could consider are the exponentially suppressed terms that there could be in these strong coupling expansions, because as you can see here, for each order in N in the large N expansion, we just considered the perturbative part at strong coupling. And so we just the power of lambda. But also here, for instance, in the SPN theory, there are, there could be some exponentially suppressed terms. And in these cases where we have truncated perturbative expansions, a method that could be useful is the one of Cheshire-Cut-Sargent, so maybe by using that. And so I think I could stop, and thanks for your attention.
Questions? Comments? Yes?
In this n equal to 2 setup, considering the first integrated correlator,
the first one
would correspond to some mixed amplitudes. I mean, what's
yeah.
Can you repeat the question?
Yes, if as we have seen this morning, there are in particular two different kinds of integrated correlators, the one with 4 mass derivatives and the one with 2 mass derivatives and 2 derivatives with respect to the complexified coupling. So Francesco was asking if one could consider also the other kind of integrated correlators and not only the one with all the mass derivatives. I think that if differently from the n equal 4, in this case, if one consider the derivative with respect to the mass, one switch on some X branch operators. Instead, if one takes the derivatives with respect to the coupling, one will switch on the Coulomb branch operators. So maybe differently from the n equal 4, one, in this case, one could have a 4-point function with 2 scalars from the Coulomb branch and one from the X branch. So maybe it's a bit complicated to give an interpretation in that way. So, yeah, maybe.
Yes, please.
On slide 11, when you showed the strong coupling results,
Yeah.
Can you give a physical reason why there should be a log lambda divergence? Because in n equals 4, we start with a large n, you have the supergravity term plus 1 over lambda corrections. What is the reason for this log lambda?
Actually, I'm not sure about the interpretation in. You mean the stringy interpretation of this result? I don't know. It's this log lambda appear also in this SPN theory, so we expected that kind of effect, but
I think Francesco is going to say.
Okay.
It also appears in n equal to 4, which I assume is something that Francesco is going to talk about.
appears, I mean, due to the presence of open strings.
Yeah.
And here, I mean, he's considering basically scattering of open strings.
Yeah.
You consider also n equal 4 integrated correlators in presence of brains, and
you get this factor.
you get also there some log lambda term.
But is this some divergence of the field theory one loop amplitude?
I would
Because
say
it's
from
divergent in 80.
I would say from the string theory. It's because also in terms of then Eisenstein singles appearing there, I mean, these modular functions are actually not really, I mean, that modular function is not properly, is actually divergent. So I think it's associated with that string.
There were some odd results by Marco. He was computing scattering from T3 brains, but I think we're going to say something like that. And the coefficient we plot of the curvature is a log of modulus of eta. It gives you the log lambda when you're going to consider this one.
So I feel this is really associated with the presence of open strings and T brains in general.
Yeah.
I can ask a question.
Yeah.
So in here, that's the exact large lambda expansion. There are no other corrections.
No, these are for the first 3 orders in the large N expansions.
Okay.
This is what
But
you get for
in
the.
your so I assume that these are all coming from what you call capital Y, which contains a single vessel. Because I'm sure from the terms that contains X.
Because in some way when you take the exact expression, X is multiplied by this kind of object that for some values it is 0 at strong coupling.
I see.
Because I also have some details about that, but it happens that we have this object in general in the exact expression, and when we use the Mellin-Barnes, for some values that appear, the strong coupling tail completely disappears. So that multiplies the double trace effect, and that's why we don't see it. And so even if we have a matrix model that also contains double traces, we cannot see this effect at strong coupling because of that. But
there is this paper by Korczynski, Zeitlin, and Korea. They were studying precisely, but they were not studying researcher's property, but they were studying these Bessel kernels. And over there, most definitely you have explanation suppressed terms.
Yeah.
But their nature changes dramatically if you're talking about localization or Kasp anomaly and so on.
So
probably,
For some specific values of N and P, it disappears. So it's and it's important because if it didn't happen, we wouldn't have got similar expansions to those of the SPM theory. So it's an explanation why even if we start from completely different matrix models, in a way, at strong coupling, they become similar because in this case, the strong coupling effect of the double traces is cancelled out. So that's why.
All right. I think it's time to thank Paolo again.
Okay, thanks.